The quotient remainder theorem. Okay, this is a biggie. We'll be using this a lot, so I'm just going to spend time slowly going through it, making sure we understand how it works, and then we'll use or explain why we want to use it. Okay, so if I'm given any integer n, so n can be negative. There is a positive integer d, so that's the divisor, just like we used to use d divides n. And there's going to be some q and r. So n is equal to dq plus r, where r is going to be called the remainder, and it has to be smaller than the divisor. So let me bring it down to earth here. So if I have n equals 14, the divisor is 3. So n equal dq plus r. So 14 will equal 3 times some q and then plus some remainder. So let's think about it. How many multiples of 3 will fit into 14? 4, right? It'll give me a 12 plus a remainder of 2. And this remainder of 2 has to be smaller than the divisor. Otherwise, it would make another multiple, right? Okay, so n div d is the number q. So that n equals dq plus r. The divisor, again, has to be bigger than 0. To be positive, so positive means not 0, right? Because 0 is not positive. And r, the remainder, is always 0, could be 0, or go all the way up to d. So if my n was 12 and my d was 3, filling in n equal dq plus r, I'd have 12 is equal to, think about it, q would be 4 and remainder would be 0, right? Because d divides n. Okay, so this we're going to use a lot in coming days. Not so much the div for the q. So n mod d. So mod is going to talk about what the remainder is. So if I'm looking at this example here, 12 mod 3. Oh, what happened there? What did I just do? Go back. All right, so, shucks, just having issues today. All right, and delete. Okay, so 12 mod 3 is 0 because the remainder is 0 when I take n and take out the divisors of d. So if I do 14 mod 3, that would be, oh goodness, where did these all come from? 14 mod 3 would be my 2, right? Because that's the remainder after I take out the multiples of 3 from the number 14. Okay, so let's just go play with some more. So here I have n is 70 and d is 9. So fitting into here, so I'd have 70 is 9 times q plus some remainder. So I know 9 times 7 is 63, and that would give me a remainder of 3. Okay, so that's a pretty straightforward one. Let's do one that's a little more, I don't know, different, right? So the divisor of 40, wait a minute. There's no multiples of 40 that will fit in, so I have 0, right? Q is 0. And then what will the remainder be? 36. Okay, so here, a little more challenging. So negative 45, divisor is 11. So 11 times something plus a remainder. Okay. So I have to have 11 times something and I have to add a remainder. So these two here are a little tricky, so I want to make sure I go over this. So I have to be able to add a remainder, so I have to go below 45. So that means I'm going to use Q is negative 5. So I get down to 55, and then I can add a 10. And this remainder of 10 is smaller than the divisor of 11, right? Okay. So 43 div 9. So this is asking for what the q is going to be. So 43 is 9 times q. All right, make that neater. 9 times q plus a remainder, right? So I know this is going to be 9 times 4. That gives me 36 plus the 7. So this is 7. So 43 mod 9 is going to be what the remainder is. Whoops, sorry. Hold on a second. I did that wrong. This one is 4. This is the q. This is the 4. This is asking what the remainder is, and that's 7, right? This one's this one, and this one's this one. Okay. Sorry about that. 30 div 2. So 30 is equal to 2 times something plus something. So I can see this is 15 and this is 0, right? So this is equal to 15. That's the number of divisors that fit inside. And this is 0. Okay, so the quotient remainder theorem lets us write an integer in lots of different ways. So if I have the divisor as 3, then any integer, this is the power here, any integer can be written as the multiple of 3, multiple of 3 plus 1, or multiple of 3 plus 2. And if I do the multiple of 3 plus 3, that gets me back to here. So all integers fit into one of these 3 categories, right? And then even think about it, if d equals 2, then n can equal 2k, or n can equal 2k plus 1. And then you know if you add 2k plus 2, you get back to here. Wait a minute, don't we know all numbers are either even or odd? So when the divisor is 2, all integers can be written as this form or this form. So we're just expanding it. So if d is 3, any integer can be written as this, this, or this. And this expands to all cases. So if d is 5, any integer can be written as this, 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 and this. How far do I need to go? Till this remainder is smaller than the divisor, right? 5k, 5k plus 1, 5k plus 2, 5k plus 3, 5k plus 4. I'm not going to do 5k plus 5 because that would get me back to here again, right? So this is how we break up how we can write different integers.